So I will start class with any questions that you may have over homework. Okay. 37? Which one was 37? Hold on a second. Is y equals cosine? Okay. This one right here? And what was it asking for? The derivative. All right. So you would want to refer to your formula sheet, which I don't believe I have mine with me. But if y is equal to cosine hyperbolic inverse of x, what is the derivative according to the formula sheet? And we didn't have to prove those. It'll be in my notes, so let me bring that up. It's not that one. Okay, hold on. Okay, this is it right here. This is the derivative of cosine hyperbolic inverse of x, right? Oh, there it is. Right, so that's your derivative. That's your general formula. So what we would be looking at here is replacing the x. I'll give you a general formula that looks a little better than this. 1 over square root of x squared minus 1. So let me change this over here to a u. The derivative will be 1 over the square root of u squared minus 1 times the derivative of u. That would be our chain rule. So for us, the u that we have is the square root of x. Okay? Does that make sense so far? Okay, so we should have y prime equals 1 over the square root of, I'll use the terminology I was using in my office hours earlier today, the argument of the function, which is square root of x, but I'm going to square it, and then minus 1, and then times the derivative of what was in here. So derivative of the square root of x is 1 over 2 square roots of x. Now you may have written that as 1/2 x to the negative 1/2, but it's the same thing. These two are the same thing. And then that would become 1 over the square root of x minus 1 times 1 over 2 root x. And I suppose there's some other things you could do to clean this up, but that would be, that would be as far as I would say you need to go. Does that match what the book has there, or close to it? Does the book have 1 over... Oh, they put the square root of x out in front of this? Oh, and then in parentheses. Okay, yeah. So same thing, yeah. And that's what it would be if you distributed the x through. Okay, does that clarify your question? Yes? Okay, so that's just chain rule. We're just applying the chain rule to the formula now. Any others? Yes. 47, if you could. What's the problem? Is that the... Oh, it's the... Okay, yeah, I just did this in my office hours, so I remember it. It was y is it was a cosine hyperbolic? 20 cosine hyperbolic x over 20 minus 15. So it's saying for this particular wire that was hanging between two poles, right? And this was 7 meters, and -7, something like that. That where this wire hits the pole or comes into the pole, we want to know what the slope of the tangent line is there, and then the angle there, right? So let me do this first. Let's make sure we all understand what the problem is asking. If I zoom in on this little section right here, if I zoom in on that, I've got the pole and then I've got the wire coming in, right, like this. And what I'm looking for is at that instant, there's some tangent line there, like this, right? There's some tangent there. And I want to know the slope of that tangent line. And I also want to know the angle, theta, that it forms with the pole. So to figure out the angle, I'm going to need to know that slope, right? And how do we find the slope of a tangent line to a curve? Well, we take the derivative, and then we plug in where we are on the curve. So I need to be able to take derivative of what's up there. That would be my first task. And then plug in exactly where I am. So where am I in this? My x value is 7, right? I'm highlighting it over here. My x value is 7. So let's start with the derivative. The derivative of this, well, 20 is a constant sitting in front of the function, so I'll just bring it with me. 20. Derivative of cosine hyperbolic or hyperbolic cosine is the hyperbolic sine, right? And then of the argument, which is x over 20. And then chain rule says I now need to take derivative of what was in here. 1 over 20, right? Everyone's okay with the fact that x over 20 is 1/20th x? So the derivative of 1/20th x is 1/20th. So I tack a 1/20th on, and then I have derivative of -15, which is 0. The 20 in the front and the 20 in the back cancel. So my my first derivative is sine hyperbolic x over 20. This represents the slope of the tangent line to that catenary at the value x. So right now I have not put in what the value of x is yet. So now I'll go grab the x. Yeah, that doesn't look right, does it? It does look like a 70. I think I put 7. I don't know. I said 20 and put 7. That happens a lot. Say one thing, mean another. All right. So let's go figure out the slope of the tangent line there. So at x equals 20, or 7, the derivative will be sine hyperbolic 7 over 20. You all have heard me say sine hyperbolic and hyperbolic sine. You all understand that I'm using those the same, right? I usually say sine hyperbolic because when I write it, I write sine first, then hyperbolic. But technically, I think in the book, they always put hyperbolic sine, hyperbolic sine. So how do I figure that out? How do I figure out what this is? Well, your calculator might have a hyperbolic sine key on it, depending on your calculator. But if it doesn't, then you have to convert this into the definition of the hyperbolic sine, which is e to the x minus e to the negative x all over 2, which is the way that I could do it. This could be e to the x. What's x for us? 7 over 20 minus e to the negative 7 over 20, then all of that over 2. And if you get on your calculator and evaluate that, you should get something like approximately, was it 3.3572? 0.3572. If you're having trouble with that part of it, just get with me. I can help you. You're good there. Okay, good. Now what we need to do is we need to try and determine what the angle is, right? What the angle is. So there might be several ways to approach the angle part of this, but I'll show you the way that I'm going to approach it. I want to go back to this picture, the one I have here. I'm going to draw it below this, all right? I have this triangle. And I want to know what this theta is. The only thing I know is the slope of this line, right? Slope of that line. And the slope of a line back from when we first learned about slope is rise over run, isn't it? Rise over run. And if my rise over run is 0.3572, then I know that my rise here is 0.3572 as long as the run I'm using is what? 1, right? Then my rise over run, even though my picture may not look like it's not drawn to scale, obviously, right? That's 1, that's obviously not 0.3572, but that picture matches the slope of that line. And so if I look at it this way, here's my angle. This 1 on the side is the opposite of the angle, and the 0.3572 is my adjacent side. So I have a trig function that connects those together, don't I? It's tangent. Tangent of that angle that I'm trying to find will be 1 over 0.3572. And I'm trying to figure out what theta is, so what can I do here? Inverse tangent on both sides. So take inverse tangent on both sides of that. We'll get theta is inverse tangent of 1 over 0.3572. And again, get on your calculator, type it in, and make sure you're in radian mode. If you want your answer in radians, make sure you're in radian mode. If you want it in degrees, then switch over. But know what you're getting, right? You should get in radians approximately, I don't remember, 1.23? What is that in degrees? Should be 7, was it 70? 70? Who worked that out with me today? What did we get? 70 degrees or 70.3 or something like that degrees? Anybody do that on their calculator right now and get one of these? You got the 1.23, right? Okay. All right, so we're good? That makes sense? Okay. The whole idea there is that we're talking about what's happening right when the wire hits the pole. So when the wire hits the pole, we stop looking at the wire as having a curve to it and look at it as its tangent line. Okay. All right. Let's get on with more stuff. If you have additional questions, you can, after class or something. I did have some students come in and make reservations for my office hours. I think it went okay. I encourage you again to get onto Canvas, schedule an appointment if you want to sit down with me. 30 minutes isn't a whole lot of time. It goes by pretty quick, but it's still, I think, a good thing. We'll see. There is also an issue where you cannot sign up for multiple sessions. So like you can't say, oh, I'm free every Tuesday at this time, so I'm going to go fill up the entire calendar for the rest of the semester. The way I think it's going to work is that you can't sign up for another one until after you've met with me for one. So I had a couple of students come in today. Now that they've already met, they can go to another one and sign up. Okay? That seem fair to you? That way no one's like hogging up the whole semester. Like you go to sign up and like, look, this person's already blocked out the entire, 3 months. Okay. All right, today we are going to finish up 4.7 and start 5.5. So we had already gotten through most of this. We had started this right here last class. And what we had established is what we're going to call in the next section the power rule. But it was a way of finding the antiderivative of powers of x. So the formula we had from last time, it was a very loose formula, but this is what we had. We said, look, if our little f was x to the n power, we said that the capital F would be 1 over n plus 1 x to the n plus 1 plus some constant. Does that look familiar? But that only worked if n was what? Anything but negative 1. Now, if n was negative 1, the antiderivative was what? Natural log x plus a constant. That's what happened if n was equal to negative 1. So we have a way of finding the antiderivative of any power of x, whether it be an integer power or a rational power. No matter what the power is, we should be able to find the antiderivative. So let's now take a look at this example. 2x plus root x minus 4 plus x cubed over cube root of x. Two x my brain is not ready to work today, so I'm going to have to switch back and forth here. Minus 4 plus x cubed. All over cube root of x. Y'all agree? I write that down okay? I had my notes printed out and I just didn't bring them. So can we use the power rule here? Well, is this a power of x? Is that a power of x? Yes. This one? It's actually x to the 0, isn't it? But we know that, remember with derivatives, if I said what's a derivative of x, everyone would say 1, right? If I said derivative of 2x, it would be 2. And pi x, it would be pi. So if you're going backwards, if you have a constant, the antiderivative is always just that constant and you throw the x onto it. So that constant, when we go backwards, should just be, antiderivative should be negative 4x. This one's a power of x, right? This is a power of x. The question becomes, or the complication here, is that the rule works if you just have a single term and it's x by itself to a power. The rule does not work if you have all these powers of x divided by another power of x. So if we have quotient here, you can't apply this rule. Not in general. But, yeah, because there's a single term in the denominator, and that's the only reason we can do this. There's one term in denominator. We can split this into 4 separate fractions. If there were 2 terms in denominator, we would not be able to do this. But because there's one, we can split it up. So I'm going to first, before I find antiderivative, rewrite the problem. 2x over x to the 1/3 plus x to the 1/2 over x to the 1/3 minus 4 over x to the 1/3 plus x cubed over x to the 1/3. So I've rewritten the cube root of x as x to the 1/3. Is everyone comfortable with that? That's just using our notation for radicals, converting from radical notation to rational exponents, converting the square root of x to x to the 1/2. So we okay there? Now, I still can't use the power rule yet because I need to resolve what each of these are. Once I have that, then I can look at each term individually and apply the rule to each one. So I have to figure out what this is here. So remembering this good old property of exponents, x to the n over x to the m is x to the n minus m, right? Subtraction. So the power on the x up top is a 1. 1 take away 1/3 is 2/3. So I get the 2 stays there, x to the 2/3. You follow? That's just this one. What about this one? What's 1/2 take away 1/3? 1/6? How do you do that? 1/2 take away 1/3. Common denominator, you could do that, right? Yes? So your common denominator would be 6, so 3 on top, 6 on the bottom, 2 on top, 6 here, subtract, right? That's one way. This is not a class for reviewing fractions, but just, you know, maybe it was a really good Labor Day weekend. Okay, what about this one? Yeah, we bring this up to the top. Now, here's a question to you. Since this x was by itself, could I just do the power rule on this right here, or do I have to bring it up? Well, when we go back and we look at this up here, we are assuming this x right here is in the numerator. So the power up here can be negative, right? But this thing is always assumed to be on top. So it's like over 1. So we never want to try and use the power rule and leave the x on the bottom. So bring it up first, and I'll put the -4 there in front of it. You said the power would become a negative. And then the last one, 3 take away a third. What is it? X to the 8/3? 8/3. That's what I'm going to find the antiderivative of. And I'm going to apply now the rule that we just talked about to each one of these. Remember, the powers I'm looking at now, each one of these are my n's, right? Those are the n's I'm going to be using. And I'm going to be using them in this formula right here. So I'll have to come in for each one of these, I'll have to put 1 over n plus 1, x to the n plus 1 for every single one. And what about this 2 that's in front of the first one? Just bring it along for the ride, right? It'll probably simplify in a second, but just tack it on. So 2 times 1 over, and then n plus 1. So what's 2/3 plus 1? Well, that's 2/3 plus 3/3. 5/3. So 1 over 5/3, x to the 5/3. That's just this first one. Now, there's something about this 1 over 5/3. It's always going to reciprocate, isn't it? I mean, that's always going to happen, but I'm just writing it down so you can see it. What about my next one? Plus, I'm working on the x to the 1/6. So 1 over 7/6, x to the 7/6. Then minus 4. Now I'm going to take the negative 1/3 and add 1 to it. So what's -1 plus 1 plus 1? 2/3, positive, right? So I'll have times 1 over 2/3, x to the 2/3. And then finally, 1 over, I need to add 1 to 8/3. So 11/3, x to the 11/3. Then plus a constant. And we're going to clean all this up. This one right here, the first one, 6/5, right? That flips up, the 2 hits the 3, so 6/5, x to the 5/3. You'll notice that throughout this semester, I will switch the way I write fractions. It's something I've always done. I've never been able to kick the habit. I switch from this to this, from the slash sideways to straight. It just depends. There's no rhyme or reason to the way I do it. It just, so sometimes it's just a matter of space. This takes up more room. So, but it's the same thing, right? All right, what about the next one? 6/7, x to the 7/6, minus 6, x to the 2/3. So that fraction actually simplified to be an integer. And last one here, 3/11, x to the 11/3, plus a constant. Box it up, we're done. And we said last class that there was one good thing about this, that you could always check your answer, right? You could always take the derivative and see if you get what you started with, and I'm not going to, but you could. Any questions on that? This is a pretty, a fairly common problem in a Cal 2 class to give something like this. It's really a good exercise with exponents and fractions, and just to get everyone kind of on the same page with the way things can work out, right? But let's look at part C. It's somewhat of a different problem here. Sine x, yes, I will. Sine x plus secant x tangent x. We good? Okay. Sine x, so little f of x is sine x plus secant x tangent x. So we need to figure out where these came from. We don't have power rule here. This is going to be completely dependent on our knowledge of common derivatives. So let's start with the sine x. What do you take the derivative of to get sine? Cosine, right? But when you take derivative of cosine, isn't it negative sine? So you're actually off by a sign. So you should make this for the capital F. You should make this not cosine x, but negative cosine x. That way, when you take derivative, you should get the positive sign to come out. Does that make sense? There's not a whole lot of work that I can show for that. Like I said, it's your knowledge of the derivative that'll help that. And what about secant x tangent x? Is that the derivative of something? Yes? What? Secant x plus c. So if you go back, you take derivative of negative cosine x, you will get negative sine x, which will be positive sine x. Derivative of secant x is secant x tangent x. Plus a constant, we're done. All right, last one. 2 plus x squared over 1 plus x squared. This is probably the most challenging one, I guess, that we've seen. Can you use the power rule, like right off the top? Can you just go, oh, power rule on that, power rule on that, power rule on that, power rule on that? No, because it's separated with quotient, right? So you can't do that. Can we do what we did in the previous problem where we split it up and just did powers and then broke them down? Not really, because we have two terms down here, right? If that was just x squared, we'd be in business, right? But because it's 1 plus x squared, we can't. Could you do this, though? Could you go 2 over 1 plus x squared plus x squared over 1 plus x squared? Is that allowed? Yes, because now you are splitting it into two fractions, but you're keeping the entire denominator there. So that's okay, but is that helpful? Well, I don't know, is it? So remember I said that there were some formulas in the book that for derivatives that you should know, antiderivatives? Yes? There's one in particular that I said try and remember. The arctangent of x, the derivative of that was 1 over 1 plus x squared, right? Remember I said that one's going to come up a lot? What about this first one right here? It's 2, right? You just pull that 2 off, and that's 2 times 1 over 1 plus. So that looks like we could handle this one with this right here. But what about the other one? We don't have a formula for that one. We do not. Do you see what I'm saying? See the difference? Why could we not do this? Why could we not just take that right here and turn that into x squared times 1 plus, or 1 over 1 plus x squared, and say to ourselves, okay, great, I know, well, first, do you all agree that this is this right here? Right? If I just, this x squared is x squared over 1, isn't it? So if I multiply, it would go across the top, 1 across the bottom, so they are the same. So do you know what the antiderivative of x squared is? Yes, 1/3 x cubed. Do you know the antiderivative of this? It's the arctangent. Don't write this down, but let's just see if that logic works, all right? This is a question I'm asking myself. If I take x squared times 1 over 1 plus x squared, and I call this, let's say we call that our little f. then is capital F equal to 1/3 x cubed times arctangent of x? Question to us. What do you think? What do you think? Let me try and help motivate the idea here. Going back to this, why is it that this made sense that when we split it all up and took the antiderivative of each one, that we were confident that that was going to work when we went back and took the derivative? Well, it was because, remember with derivatives, if you have pluses and minus between things, you just take derivative of each one, right? Each one, and just add all those answers together, correct? The problem with this one is that if you take this right here and split it up into a product, right? And then say, all right, I'm just going to take each one and take the antiderivative, then to check our work, we must take the derivative of that, right? When you take derivative of that, do you just take derivative of the first one and multiply it times derivative of the second one? No, you have to use the product rule, don't you? Right? And that's going to be the most challenging part of this class, at least up through this whole chapter with trying to find antiderivatives. Because when we did derivatives, right, in Cal 1, we said derivative of a sum or product is clean. It's just do each one. But when we got to product rule, we realized, look, you don't do the derivative of each one. You do derivative of the first one times the second one plus the derivative of the second one times the first. Then we got to quotient. It was like f prime g minus g prime f over g squared, all that weird stuff, right? It didn't work out naturally the way we thought it would. So when we're trying to undo it, it's going to be a disaster. Because you're trying to undo the product rule, and you're trying to undo the quotient rule. And later on, we're going to be trying to undo the chain rule, which is even more challenging. So this is not going to fly. Do I need to check it? I mean, what would be the derivative of this? Derivative of the first one is what? If I take this derivative, so f prime, it would be x squared times arctangent x, right? Plus, now derivative of arctangent, which is 1 over 1 plus x squared, times the first one, 1/3 x cubed. Is that right here? This right here? No, they're not even close, are they? This is not that. So that didn't work. So coming back up here, sorry if I'm kind of going all over the place here. Go back and watch the video, I guess. This one was fine, right? This one was fine. That one is not. So I'm going to restart the problem and just show you something else that might work. Unless somebody has a suggestion. Good. Who said that? So why? What makes you think that? Okay. So long division, because they're both polynomials, they have the same power. So if we do long division, this should reduce out to be something. All right, let's see. How do we do long division? We do put them in descending order, leaving spaces for any powers that we don't have. On the I did this backwards. Sorry, apologize. That's wrong. It's x squared plus 2, right? And then on the outside, it's x squared plus 1. Why did I leave the gap there? Because I don't have any x terms, right? But I need in division to leave a space so that I can line things up. So the way we did long division, we say to ourselves, how do I turn that highest power of x in the thing I'm dividing in, right, into the other one? So what do I need to multiply x squared by to get x squared? 1, so I just put a 1 here. I can put it right there. Then you're to multiply that 1 to each of these and put them underneath and line them up. So 1 times x squared is x squared. That goes here. And 1 times 1 is 1, right? And then we come through and change the signs. And then we add down. So what am I left with out here? These cancel. I get 1 out here. And then I ask myself, how do I turn the x squared into 1? And at that point, I can stop because the power out here is now smaller than this power. So my remainder, I put out here plus, my remainder is what? 1, and then over the divisor, which is x squared plus 1. If you need to go back and watch long division, go find long division somewhere. Long division of polynomials. If you need to go refresh yourself. So this blue expression, this f of x, is actually just 1 plus 1 over x squared plus 1. Are we happy with that? Yeah, I mean, look, this is going to be easy to take, well, easy, sorry. This is going to be nicer than the other one because do you know what the antiderivative of 1 is? X. Okay, and it's separated by addition, so I can do these separately. Do you know the antiderivative of 1 over x squared plus 1? Arctangent of x. So now our capital F will be x plus arctan x plus c. Could you check it? Yes. If you check this, you're going to get this, right? How do I know that that's that? How could you turn this one right here? How could I turn this back into this? How do you do that? How about just get a common denominator between these? Yeah. So I could rewrite this one here as x squared plus 1 over x squared plus 1, right? And now combine them together, and the top would be x squared plus 2 over x squared plus 1, and they're the same thing. So you see how that little subtle algebraic move made the problem so much easier? I'm trying to figure out what made you think to do that. I mean, just like you saw that you could do division? Okay. So what we need to start getting used to in this class is the idea of hitting dead ends, because you'll hit a lot of dead ends, and just trying something else and not giving up. Because that I think is one of the biggest skills that you can gain in this class is we're going to be trying to find antiderivatives for the next few weeks. And some of them you're just going to keep trying, it's not going to work, and try something else, not going to work. It's just you got to be persistent. Keep going after it, keep attacking it, different approaches. All right? All right, now that we've kind of talked about some antiderivatives and some ways that we can attack them, let's see some results of this. This is called rectilinear motion. Recall that if the position of an object which is moving in a straight line is given by the function s equals f of t, which we call the position function, then the velocity was the derivative of its position function, and the acceleration function was the second derivative, or the derivative of the velocity. Y'all seen that before, Cal 1? Okay, so this, or physics, yeah. It kind of makes sense. I mean, this thing always kind of made sense to me as a student. I don't know if it does to you. But just think about an object. If this is time, and this is position, and I tell you exactly at every point in time where something is, in other words, I can draw a curve that tells you exactly where an object is at every point in time, then it would make sense that I should be able to tell you its speed at every point in time. And I should be able to tell you its acceleration. Because knowing exactly where something is at every point in time, that's a lot of information to have, don't you think? That's what Cal 1 taught us. If you know where something is all the time, you can tell me its speed and its acceleration all the time. What we're now going to discover, and I always thought this was a little odd, not odd, but kind of amazing, is that if somebody gives us just the acceleration, so it doesn't tell me anything about its speed, doesn't tell me anything about where it is, it just tells me what its acceleration is at every point in time, then I should be able to go backwards and recover its velocity, and then go backwards again and recover its position. Shouldn't I? By just doing antiderivatives. But there's a little bit of an issue here. Because, I mean, I think if I told you right now that an object was moving in a straight line and if its acceleration was this, there's no way you'd be able to tell me where it is. Right? Because you could have two different objects in two different places doing the exact same thing. You can't recover where they are until I give you just some more information. So remember that every time when we go backwards with the antiderivative, we always have that c, don't we? That constant that we don't know. So what it's going to require is for us to nail this function down exactly, someone's going to have to give us just a little bit of information to be able to nail down exactly what function it is. And what I think is amazing is that we only need two pieces of information. We just need to know its speed at one point in time. That's it. Just tell me how fast it was going at one point in time, and tell me its position at one point in time. If you give me that, I'll get everything else. Doesn't have to be the same. Nope. So you can either give me the velocity at one point in time and then the speed at the position at one point in time, or you can give me its position in 2 points in time. Either one of those is enough for me to be able to recover the function completely. So let's see how it's going to work. If the acceleration of an object moving in a straight line is given by a of t is 24t minus 6, and s of 1 is 7, and v of 2 is 41, find the position function of the object, and then find its position at 2. So I didn't give you any units here like feet or seconds or anything like that, but let's just take it arbitrarily here. So let's work this one out. 24t minus 6. So I'm giving you that the acceleration as a function of time is 24t minus 6. I also give you that, what was it? S of 4 is 7? No. F of 1 is 7 and V of 2 is 41. Okay. So look what I've given you. I've given you an acceleration function, right? It's telling you exactly the acceleration of this object at every point in time. And I've told you S of 1, which is the position of the function at exactly one point in time. And I've given you the velocity of the function of the object at exactly one point in time. Make sense? Okay, let's see how we can recover the position function. So let's first go backwards and find my velocity. The velocity function should be the antiderivative of this, right? The antiderivative. So what is the antiderivative of 24t? Notice we're using t naught x, right? 24 comes out in front. Antiderivative of t to the first power. So you do the 1 over n plus 1. So 1 over 2 t to the 2. Right? We're adding 1. Now, what's the antiderivative of negative 6? Negative 6, and in this case, t, we're using t. But because it's an antiderivative, I always have to tack onto this what? Plus some constant. I'll clean it up. 12t squared minus 6t plus some constant. So I know last class I showed you an image. I said when you talk about antiderivatives, it gives you this whole family of functions, right? Any of them will work. Here's my family. But this is a particular object, right? This is a particular object, particular situation. So I need to narrow it down to one of those functions from the family. So I need to figure out what the c is. So now let me go up to this information that I have up here. I do know something about its velocity, right? When I plug in 2 for t into the velocity function, right, it should spit out 41. So if I come in here and I say v of 2 equals 41, that should mean that when I plug 2 into this, right? So when I have 12 times 2 squared minus 6 times 2 plus a constant, that should all turn out to be 41. And now let's just do some math here. 2 squared, 4 times that, 48. Take away 12. What do you have? So 40, so yes, you're ahead of me here. 12. Right, that's where we are, and then just move it over and you got C is 5. So now what I've done is instead of telling you, hey, the antiderivative of this, the velocity function, comes from a family of functions, I know exactly what function it is. Exactly. It has to be this one. So C has to be 5 for this to work. So now I'm going to rewrite the velocity function in its final format. It's 12t squared minus 6t plus 5. box it up just because that's what I'm going to be working off of to go to do the next thing. So now from here we want to recover position. So we're just going to repeat the process, right? So when I repeat the process here, my S of t will be the antiderivative. So 12 times 1/3 t cubed minus 6 times 1/2 t squared plus 5t plus c. Now I'm going to use d instead just because I don't want to confuse the c up there with the c down here, and just to be, you know, kind of separating things out. All right. I could have, and it wouldn't be bad notation, called that c up here c1 and called this one down here c2. That would be good also. But I'm using c and d. Why would c1 and c2 be better than c and d? Yes, I'm saying like letter-wise, C and D works just fine, but why use C1, C2? Why do math people like to do C1, C2 instead of? Yes. Mhm. Correct. That's a good correspondence. That's not quite what I'm getting at though. Why not use, like, if I had to do an antiderivative again, I could do C, D, and E, right? And what if? Yes, this is a more abstract idea, though. I mean, everything that everyone's saying is correct, but why is it that mathematicians love to use subscripts like that instead of just using letters? Because we're lazy, yeah, and we like to make things look complicated. No, there's a major reason, okay? There's a major reason, because we like to generalize things, okay? Mathematicians like to generalize. We like to find ways of finding formulas that apply to everything, not just one situation. So what happens if I have to do this? Let's say there's a particular problem where we're no longer talking about velocity and acceleration, but we have to take an antiderivative 100 times. What's going to happen? You're going to run out of letters, right? If you start using C and D and E, you'll run out of letters. You only have 26 to work from. You're already using some here, so you run out. But if I subscript C1, C2, C3, I will never run out of constants. All right? You may remember that when someone defined what a polynomial function was, they said f of x was a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 until you get down to a sub 1 x plus a sub 0. Anyone remember that general definition of a polynomial function? How about this for a quadratic function? Ax squared plus bx plus c. Y'all remember that? Okay, we used a, b, and c for quadratic because the highest power was 2, so we say a, and then next power down b, and then c. But what if this was a to the 100th power? Then you couldn't use a, x to the 100th, b, x to the 99, c, you know what I'm saying? Because you'd run out of letters. So this is more powerful. X can be any power. This is just the number in front of it. So if that's x to the millionth power, this is the a to the subscript million. The next one would be 9. Yes or no? Does this make sense? Okay. I just want you to understand. I mean, it's not because math people like to make things look more complicated. There's always a reason behind it. All right. Now, put that together. S of t equals 4t cubed minus 3t squared plus 5t plus d. Did you already get it while I've been up here yapping? Yes? Okay, so we had plugged in, well, we know that when we plug in 1, we need to get 7, right? Is that what we're using? So when you plug in 1 here, you get 4 times 1 cubed minus 3 times 1 squared plus 5 times 1 plus my d must be 7. So 4 minus 3 plus 5 plus d must be 7. 1, right? D is 1. So that means my position function, my final position function, S of t, is 4t squared, or t cubed, minus 3t squared, plus 5t, plus 1. Box it up. Questions? I haven't answered the problem completely yet, because there was also something else that was asked, right? Said, find the position function. We just did that. Find S of 2. So tell me where this thing is at 2 seconds or 2 hours, whatever that is. So all you're going to do now is what? Plug 2 into this function right here. Because you should be able to tell me now exactly where this thing was at every point in time. Any point in time. Plug it in, boom, we're done. All right. While we're on this topic real quick, because we're getting ready to get out of this section, I just wanted to bring something up. Has anyone ever seen this formula, maybe in a physics class or something like this, like that? Anyone ever seen something like that? It's a formula that tells you how high an object is off the ground if you're dropping it on Earth, if you take air out of the equation. So in an airless environment on Earth, you drop an object, that tells you where it is. Where D naught is how high it was to start, and V naught is what we call the initial velocity. But watch this real quick. If I take the derivative of this, what do I get? Negative 32t plus what? V naught is a number, right? V naught is a constant. Derivative of this would be V naught, and derivative of D naught would be what? 0. Okay, take derivative again, that's acceleration. So you get negative 32, and that's it. Because on Earth, the only acceleration that we have when you drop an object is what? Gravity. So that's the acceleration of gravity in feet per second. In a lot of physics class, it's meters per second, right? 9.8 meters per second. So if you convert 32 feet over to meters, that's what you have. This is the feet formula. But watch, if we would have gone backwards, right, what's the antiderivative of this? Well, this right here, right? What's V naught then? That's our constant of integration. I don't know what that is, but that's that initial velocity. Why is it the initial velocity? What would happen if t was 0 here? Isn't t 0 when I'm going to start to drop it? If t is 0, then v of 0 would be negative 32 times 0 plus v naught, right? So v naught, that's going to be my starting speed. It's the speed of the object at 0 time, so that's my starting speed. Then if I integrate that again, I get this, and this d naught is going to be my starting height. So you can basically start with just knowing the acceleration on the planet, and it doesn't matter what planet you're on, and you can go backwards and recover the position function. So all that changes, you go to the moon, that number changes. Or this number changes, and then that one changes, and then they all change, right? You go to a different planet, that number changes, but they all have the same position function for falling objects. Just a little random piece of information there. All right, that's the homework for that section. And now I'm going to start 5.5. I said in the beginning of this class that I'm teaching this Cal 2 a little different than I normally do it, right? I told you that. As you can see, we're kind of all over this book. We're going to do like all of chapter 5. Is it 5? Yeah. Then we're going to go, because we're at 5.5 now, right? We're going to do all of 5. We're going to go back to 5.1 later. It's a little odd, but I'm trying to follow, like I said, everyone's plan here. See how this works out. Substitution rule. All right, before we can begin this section, I need to establish some notation. Because earlier in Chapter 5, they established this notation, but I need to establish it now because we haven't looked at it. Right now, if someone gives you a function, little f, I've said the antiderivative is capital F, right? But how do I tell you to go find the antiderivative? I have to write down, find the antiderivative, right? Instead of writing down, find the antiderivative of little f, I can use this notation right here. I put this little symbol in front of the little f, so here's my function, and then I tack on this little thing here. And that will be your capital F plus C. This whole thing, all of this right here, right? All of that is called the indefinite integral. The indefinite integral. The symbol in front is called the integral sign. The f of x is called the integrand. It's very similar to like when you have radicals. The thing under the radical was called the radicand. The thing inside of your integral is called the integrand. The dx that's tacked on to the end of this is purely there for notation right now. It's called the differential, and we're actually going to explore that in detail later. It's very important in the problem, but right now it really doesn't make a lot of sense as to why it's there. All right? But it has to be there. When you write an indefinite integral, you always have to include the differential. This kind of tells you right here what your independent variable is. Right? So you can kind of see it from here. I'm saying I have a function of x, right? X is the variable. Capital F, of course, we said was the antiderivative, and the constant over here we call the constant of integration. The process of finding antiderivatives of function is called integration. So back in Cal 1, when you were finding derivatives, that was called differentiation. Now what we are doing is integration. The power rule for integration we've already seen. If you're trying to find the indefinite integral of x to the n dx, it's one of those two cases, right? Depending on the power. Oh, that's a typo. Y'all see it? That's n, right? And over here, n, and that should be negative. Agreed? If the power is not equal to -1, we can use that. If the power is -1, we have to use that. So that's nothing new there. Common antiderivatives. So I've posted on our website under files the formulas, right? And on page 6 of the formulas, which is the last page, there are 20 formulas for antiderivatives for integration. You should become very comfortable with these. At least knowing that they exist on this page is the most important thing, is knowing that they're here, all right? So bring that to class from now on. A lot of times what I'll do is I'll just say, oh, you know, we're working this problem out, and then, okay, that's formula 13, as you can see. So right now, if we want to find an antiderivative, right now, we have really a couple of things. The power rule, which means we have to have x to a power, right? Or we have the common ones like I could find the antiderivative of cosine because I know the derivative of a sine is cosine. Or I could find the antiderivative of secant x tangent x because I know the derivative of secant x is secant x tangent x. I can find the antiderivative of 1 over 1 plus x squared because I know the derivative of arctangent is that, right? But outside of those very few integrals, I don't really have a technique for finding antiderivatives. In Cal 1, we had techniques for almost everything, right? We had any power we could take derivative of. If we had products, we could do it. Quotients, we could do it. Chain rule, we could do it. It was always very methodical, right? Do this and this and this, this and this, done. This integration is going to not be that nice. I already said that. And here's the first rule that we have, other than the power rule, the first real technique for attacking integrals. It's called substitution. We just call it substitution. They call it substitution rule in the book, but we will just call it substitution. And it's basically trying to undo the chain rule. So I'd like for us to start with this right here. I would like for everyone right now to find the derivative of sine of x squared. What is the derivative of sine of x squared? So what rule are you going to have to use here? Chain rule, right? The derivative of sine of something is cosine of that something, or cosine of the argument, times the derivative of the argument. The derivative of the argument is what? 2x. So this is really just 2x cosine x squared, right? That's the derivative, not antiderivative, that's the derivative. Rhetorical question. How comfortable are you with that? Because that is directly related to the next thing I want, which is for us to find the antiderivative of x cosine x squared dx. Two different problems, right? First one, take derivative of sine x squared, you get 2x cosine of x squared. Now, I've almost given you our answer there, right? It's almost the same thing. What am I missing here? The 2, right? I have an x, not a 2x. It would be reasonable to think that the antiderivative of that should be really close to sine of x squared, right? How do I get back to it, though? I mean, are you just going to look at that and go, sure, that's sine x squared, and then I'm off by a little bit? I mean, so we need an approach, don't we? So here's what substitution is all about. Substitution is the most basic strategy we have, all right? We're going to have several strategies. We're going to have substitution. After substitution, we're going to have integration by parts. After integration by parts, we're going to have trigonometric substitution. After trigonometric substitution, we're going to have partial fraction decomposition. And I'm missing something. Oh, trig integrals. We're going to have all these different techniques, depending on the integrand, how to attack it. Substitution is like knowing how to open your toolbox. You got to have this one or you can't do any of the others. So here's what we do. The general strategy, and there really isn't like a fixed thing. You look at the integrand, right? You take a look at it. Just take a second to kind of investigate the pieces of it. And you try and see if you can find something. I don't care what it is. And so you see something, and you also see its derivative there. Somewhere else in the problem. Somewhere else in the integrand, you see its derivative. Now, the derivative that you see has to be in the numerator for this to work. And then the derivative that you see could be off by a constant, and that's still okay. And then what we'll do is we're going to make the substitution. We're going to let u be that something you saw from part 2, and then go for it. So let me show you, okay? But that's the step. Those are the steps. So back to this. Forget that exists up there. Just look at the blue. Do you see something and its derivative? Close? What do you see? Okay, you see x squared? Everyone see x squared? What is its derivative? 2x, right? 2x? You have x. It's not 2x, but it's x, right? So you're off by a constant. Is the x that you see in the numerator? Yes, because this is really over 1, isn't it? So it's satisfying everything. We see something, x squared. We see its derivative off by a constant. That's all right. And it's in the numerator, so we're happy. So what we're going to do is we're going to let u, here's my substitution, going to let u be equal to the something that you just saw, which was what? X squared? Now, watch carefully. Once you determine what u is, I'm doing this as scratch work on the side, okay? I want us to find the derivative of u with respect to x. What would the derivative of u with respect to x be over there? 2x, right? Now what I'm going to do, something that we didn't do a lot in Cal 1, is I'm going to rewrite this as du equals 2x dx. Really what I'm doing is I'm kind of like multiplying both sides of this equation by the differential dx. So it cancels on the left and appears on the right. Everyone see that? Now we play kind of a mix and match game, all right? We already know that x squared here, right? X squared right here is right here. So I will be able to replace that with the letter U. I will substitute that out for U, right? The question is, though, what do I do with all this other stuff? So look at this. I have an X, right? And I have a DX all together on the same line, right? So you could, I don't want you to rewrite this way, but I want you to see it at least. It could be rewritten this way, because it's all multiplication, right? That X could be slid to the back like this. Now you have over here an X dx, don't you? You just don't have the 2 in front of it, right? You don't have the 2. So what I'm going to do is right here on this equation, I'm going to multiply both sides of this equation by 1/2. So what happens is I get 1/2 du equals what? X dx. Now do these match exactly? Yes? Any questions on what I've done? No questions? Yes, that's right. What I'm going to do, though, is I'm going to now rewrite the whole problem. And when I rewrite the entire integral, I should no longer have x's. Everything should be in terms of u. So let me try this. Do y'all want to work off the one that I rearranged, or do you want me to go back up here? The rearranged one? Okay, maybe because we're starting this, we'll start with the rearranged one. Okay, if I rewrite this problem, I'm going to put an arrow because I'm rewriting it. It's the integral of what? Cosine u, right? That's cosine u. Times the x dx is going to turn into du over 2 or 1/2 du. And what do we know about, is that all? That's it? We're done with that? That's it, right? This is exactly half of du. This is exactly cosine u. And now the 1/2, because it's a constant, can come out, right? Integral, just like with derivatives, constants can come out. We can bring that constant out. Right? When you take a derivative, won't that constant just come along the whole time? So when you do the antiderivative, it comes along with you also. So I'm just going to pull that 1/2 out. And now what we've done is we've reduced this somewhat complicated problem into this. Do we know the antiderivative of cosine u? So what do you take derivative of to get cosine u? Sine u? Just sine, right? So this should be equal to 1/2 sine u plus a constant. So look what's happened. The integral just told me what? Find the antiderivative of this, right? Forget the du, just find the antiderivative of that. What's the antiderivative of cosine of u? Sine u. Then I added the plus c, and then I tacked the 1/2 on out here. Do y'all follow that? Now we're not done, because the original problem said, what's the antiderivative of cosine x squared, right? Or x cosine x squared dx. Everything was in terms of x. My answer is in terms of u. Right? So that's like me saying, what's your favorite color? And you're like 10. You know, we're not talking about the same thing anymore, right? We started with x's. We need to end with x's. So let's say, what is it? 1/2 sine what? U is x squared, right? That's what u was, so I'm switching it back, plus c. Now check it for yourself. Well, we can check it. What is the derivative of this? Well, forget the 1/2. What's the derivative of sine of x squared? Cosine 2. We did that earlier, right? And then take half of it, and what do you have? Just x cosine x squared, which is exactly what we were trying to find the antiderivative of. That's the method. That's the technique. Yes? Very good question. This is the confusing part of this notation. When we look at this notation, this symbol is telling you find the antiderivative of this. This right now for us keeps track of what our variable is. When you go back and take the antiderivative, you don't worry about it. It's gone. It goes away with the integral sign when we go backwards to the antiderivative. But you see, it has to be there because it was there right here, right? And it helped us with this matching game that we played. It had to be there. Okay, here's why. Let's look at this right here. If I ask you to take derivative of that right now, you would say 1/2 cosine u, right? But chain rule would say then take the derivative of u, right? So it would be like a u prime. Well, this is kind of like your u prime. See what I'm saying? Now, sometimes that u prime is just 1. Sometimes that u prime is not just 1, it's something else. For us, in this problem, when we said dx here, dx was really 1. We didn't realize it was 1. But du here is not 1. du is 2x dx. So this differential, sometimes it's 1, sometimes it's not, but it comes from the chain rule. When you take the derivative, it's always sitting there next to it. I hope that makes sense. It's going to take some getting used to the notation of it. All right, shall we try something else? Yeah, of course. Oh, by the way, in my notes, that's the end of the notes right there. It's kind of like, someone says, okay, yeah, you get on the bike, you start pedaling, and you just go. I mean, that's kind of what it is for this section. I've given you the basic idea, and now the only way to learn is to get out there and just do a lot of problems. And I mean a lot. If you've never done substitution before in your life, then you should probably do 100 to 200 problems before you can say you feel good about it. All right? I mean, really, you should do a lot of substitution problems. It'll never go away. For the rest of this class, substitution will never go away. Later on, what we'll do is we'll get to problems that are really complicated, and then when we get to the point where we see substitution, we stop. We say, okay, from there it's just substitution. So we want to be able to be comfortable with it. All right. So this is the part of Cal 2 I think that is the most difficult, meaning that I can't teach intuition, right? I can't teach intuition. Intuition just comes from, like I said before, how comfortable were you with Cal 1? That usually indicates how good your intuition is going to be here. I've tried to give you some steps. Let's see where we can go with it. So does anybody see this as a substitution problem, or do you see it as the power rule that we did before this? Power rule? How are you going to do power rule here? Can you do power rule? Why can't you do power rule? Because there's two terms on the bottom, right? So you can't split this up? How about long division? Why not? Bottom power is bigger than top, so you can't do the long division. You could set it up, but you would be stuck right there. So that's not going to work. Anyone see anything else? Okay. So you're starting, good. These are the things that you should start seeing. I see 1 plus x squared. I'm thinking arctan, right? Except for the x up there, of course. And we can't peel the x off because we just said a little while ago, if you could do that, life would be nice, right? Just put in 2 different things, do antiderivative of each one. Can't do it with a product. So yes, arctangent looks maybe like it's promising, but now let's think of it from the substitution point of view. Do you see something and its derivative? Okay, you see x squared. What's its derivative? 2x, right? Do you have a 2x up there? You have an x, you're off by 2 again, right? Just so happens. Do you all agree with that? Don't write this down, not because it's wrong, but don't write it down. You're saying that possibly that would work because the derivative, and watch the way I write this. What have I done there? I already moved the dx over. I'm going to do that every time, okay, because it's always going to be there for us. So u is x squared. We said that looks like it might work. Then the derivative of that is 2x dx. I have an x dx. Is my x, and my dx is always in the numerator, but is my x in the numerator? Yes. So I'm okay with that. I'm off by a constant. It looks like that might work, correct? However, anybody have anything additional that you might want to throw in? For what, are you? Well, that's x to the negative 2 if you were able to move it up, but you can't move it up because it's attached to the one with addition. So you can't bring that up. It's not in the numerator, so I'm not sure I'm following. Was that? Oh yeah, no, one of the stipulations was that the derivative should appear in the numerator, not the thing you're calling u. Okay? So you find something and its derivative. The something we found can appear anywhere. Its derivative has to be up top. There's something else. I'm trying to see. Right now, we could do this problem. We could finish it off just like this, but there's something more. You grabbed for the x squared, right? We will, yes. But you grabbed x squared because the derivative of that was 2x. You saw that, right? Grab a little more. How about if you let u be the x squared plus 1? Would that make any difference with the derivative? No? It wouldn't, right? What's the difference between that, though? Right now, if I write it as is, I will be able to replace the bottom with what? 1 plus u, right? But if I had called this, over here, I'm adding this to this, x squared plus 1 instead, I'm not changing the derivative, right? Derivative is still going to be the same, but now I can replace the entire denominator with what? U. So this is kind of like this balance game you have to do in substitution. You want to try and grab something that you see it in its derivative. You want to grab as much as you can without grabbing too much. And you'll know if you grab too much because when you go take its derivative, it makes the problem all wacky and crazy. So do you all agree with that? Okay, let's work this out. I am now going to be able to replace x squared plus 1, right? Right here, x squared plus 1. That's going to be a u, isn't it? Now, my x dx right here needs to match up with that x dx right here. So I'm off by 2. So again, I'll multiply both sides by 1/2. It won't always be 1/2. So I will be able to replace x dx with 1/2 du. Watch the way I write this out. I'm not substituting yet. I just, again, want to make sure baby steps here. That's the way I've really ripped this integrand apart. I've slid the x out here with the dx, which left me a 1 over this. Yeah? Now my x dx matches up out here. My 1 over 1 plus x squared is there. Now can I rewrite it? All right. This is going to become 1 over what? U times 1/2 du. Is it all right if I pull the 1/2 all the way out now? Okay. Good. Whenever you see 1 over u du, it should be automatic. That's natural log u. But then we have a 1/2 in front. This is really u to the negative 1, isn't it? And we said that's power rule, but whenever we have negative 1, it's always natural log. So this is 1/2 natural log u plus a constant. But what is natural log, what is u? The u that we chose was x squared plus 1, or 1 plus x squared. If you enjoy math because of the part of math that can be kind of like a puzzle, and you're trying to put things together, you'll enjoy substitution. So if you like puzzles, but if you don't like those puzzles where they're real tiny pieces and there's like 40,000 of them, you may not like this class later. For right now, we're working with, the puzzle has a finite number of pieces. I mean, really, that's what it is, this class. The integration, you've heard that this class is hard. This is really why. Because right now, the integration we're doing right now, there's only one way to attack this problem. Well, power rule, a couple of formulas, and substitution. That's all we've got. Your first test is going to cover all 5 techniques of integration. All 5 techniques. So when you get to that first test and you give a problem, you're not going to be prompted by use substitution to find the antiderivative. It's just going to be find the antiderivative. Which technique? That's all going to depend on how many problems you did, how quickly you recognize the patterns, the techniques, and how comfortable you are moving through them. I didn't make the subject up. Sorry, it's just the way it is. All right, let's try something else. Can I borrow someone's book? Someone might have it out right here. Here, I've got one right here. Let me see. I'll pick some problems right out of this here, 5.5. That's a good one. I'm just looking at some even problems here. Remind me to get that back to you. How about this? Just cancel the root x's. What would that be if you did that? What do they say? To cancel that, it would be sin. That'd be sin. I don't know. You tell me. What do y'all think? Yep, it is a product. We're trying to undo it, right? And that's the challenge. Can you do just power rule on this one? And we have a product. You cannot just do power rule on this and then your own thing. You cannot do that. So when you're looking at what your options are right now, you really only have one, and that's substitution. So in order to use substitution, you have to see something and its derivative. What happens if you don't see something and its derivative? You just have to try something, right? I said go for it, right? At some point you gotta take a swing. And we're going to even see problems that we'll do them later as we go on where it's a substitution problem, but you don't see something in its derivative. It's not there. You don't see it. It's hidden. But you still do it, and all of a sudden, boom, everything pops out, and it just works. And you're like, holy shit, how'd that happen? And you're just like, well, because I tried, right? You have to try something. So what do you want to go for here? Square root of x is u? Does that seem natural as a choice? Okay. Does this seem natural as a choice? Why not? What's the derivative of this? It's chain rule, right? Cosine. You don't have cosine up there. So you see what I'm saying? There, I grabbed too much. How about this? Would this be a good choice? U is x. No, because the derivative of x is 1, and that actually would just take you back. All that would do, if you did this, all this would do is you would rewrite the entire integral and all your x's would become u's. It'd be sine square root of u times 1 over square root of u du. And you'd be at exactly the same spot. So that's an example where I didn't grab enough. In the previous, what I wrote down, I grabbed too much. So I try the square root of x. So now let me take derivative of that. The derivative of that, because again, we've become very, very comfortable with derivative of square root of x is 1 over 2 root x. As opposed to this, I've been trying to give like subtle hints to people that you need to probably stay away from this notation for the derivative of this, because this rarely appears in an integrand. This will be an integrand all over the place, and it's easier. You recognize it better if you're taking the derivative this way. Am I making sense? What am I missing off the end of that? Dx? Okay. Do we have that? Pretty dang close, right? We've got the square root of x. That's going to be replaced right there. Hey, why am I not replacing that with u? You know what I'm saying? Like, this is u, right? Why not replace that with u also? Yeah, it's there. It's going to help us with this, right? If you take that and make that a u, watch. If you say, I'm going to come in here and make that a u also, then we've got to find a replacement for dx, don't we? And that means we got to replace it here, which means we got to put this root over here on this side. You see what I'm saying? It would still work, but I'm trying to get you to see that it would take a little longer. Yes. If we see that root x out there, that 1 over root x as being part of our du, this is going to work out a lot cleaner. So I have my 1 over root x dx. I just need to resolve the issue of this 2 down here. So how can I get rid of it? Multiply both sides by 2. So I get 2 du is 1 over root x dx. And that's an exact match of what's there. Shall we rewrite now? Integral. Then what? 2. Okay, you want 2 out there now? Sine u du. What's the antiderivative of sine of u? Antiderivative of sine u. Negative cosine u. So this is negative 2 cosine u plus a constant. So at this point, when I actually take the antiderivative, is when the integral sign drops and when that d whatever drops out also. And I have my plus constant. Am I done? Nope. Switch back. What's u? Square root of x. Let's turn the screws a little bit. I'm going to try and do 2 more examples. And because we only have 10 more minutes, I'm going to move a little quicker through this by guiding you faster here. Do you see something in its derivative? Well, does anyone know what the derivative of 3 to the t is? What's the derivative of 3 to the t? It's itself then there's something else you have to throw onto this. Natural log 3. On your formula sheet, you have something that says this. The derivative of a to the x is a to the x natural log a. That's a derivative formula from Cal 1. Now, if it's e to the x, what is it? E to the x natural log e, but what's natural log of e? It's 1, so that's why it's not there usually. But for a general exponential, it's got to be there. So if I look at this, 3 to the t right here, the derivative of 3 to the t is 3 to the t natural log 3. Natural log 3 is a constant, isn't it? So I've got it up here, don't I? But it's off by a constant. That I'm okay with. So how about letting u be 3 to the t? Plus 4? That's even better, right? Why don't I grab the whole denominator? Let that be my u. Then my derivative, we said, would be what? 3 to the t natural log 3 dx. Just don't forget that dx out there. Dt. Sorry. dt. My variable is t. So my entire denominator here, right here, is accounted for. The 3 to the t dt is 3 to the t dt there. So I'm going to have to divide both sides of this by what? Natural log 3 to get it to match up. So I should be here, 1 over natural log 3 integral 1 over u du. I moved through that quickly. I recommend you go back through and maybe run through it again on your own. Try and replace everything. Make sure you're comfortable with it. 1 over natural log 3. 1 over natural log 3. It's my constant. What's the antiderivative of 1 over u? Natural log of u. So natural log of u, but what's u? 3 to the t plus 4, then plus our constant of integration. I moved through that quickly, but I did the most important thing for you, and that's at least set up what u is. From there, I think you should go through and just make sure you're comfortable with everything I did. There's 2 more that I think are great. I'm going to try and do them. I know some of you are still writing, but you can go back. Look at this one. Where is it? I think we can kind of start at this point just looking at it and saying, well, that's definitely not power rule, right? You got that thing stuck in the bottom under a root. I mean, there's just no way you're ripping that thing apart and splitting up into powers of x. So we go with the substitution. So you're trying to find something in its derivative. X cubed. The derivative of x cubed is 3x squared. Do you have x squared? Yeah, but look where it is. It's not only is it in the denominator, it's trapped underneath the square root, right? Which is even worse. Honestly, it's even worse. You see what I'm saying? Because if you did x cubed, this right here would be replaced. This would have dx in it. Dx would be trapped on the bottom, and dx needs to be up top. So it just would not work out that way. So the natural choice doesn't seem to work. So what do you think then? I don't know. Well, remember I said you have to swing, you have to do something, right? What? X squared? Okay. X squared, possibly. Let's go for it. We're taking a swing. What is the derivative then of that? 2x dx. Do you have 2x dx? No, but you do. Because the top can be rewritten as x squared over square root x squared plus 1 times x dx. Can't it? Because x cubed is actually x squared times x. So you could peel one x off because it's multiplication. X dx can be this, and then you'll have to bring the 2 out over here, right? You see that? Now this down here, x squared plus 1, we're going to replace the x squared with what? U. What about this x squared? U, right? I mean, x squared is u, isn't it? So this will be u. This will be square root of u plus 1. And this will be, 1/2 du. So I'm going to come back over here. I'm going to get that 2 out of there. Let me try and match things up now. This x dx is right here. We set our x squared. I'm going to replace this one and that one with x squared. With u. Follow? Now, let's just do that. I don't want to go backwards now. So here we go, rewriting the integral. We have 1/2 come out. On the top, u, bottom, square root of u plus 1, du, right? Du. Where? Right here? X dx got replaced with 1/2 du. The 1/2 came out, the du's here. And that would be a red flag. If you ever write out an integrand, rewrite it after you do a substitution, you've got u's and x's mixed together, something's wrong. Something's messed up. You can only have one variable at this point. In Cal 3, you can have multiple variables inside there, and that's a whole different animal. Well, as great as that looks, it doesn't seem to have made that integration any easier, does it? It appears to me that that's still not a simple problem, right? Do you see something in its derivative? You would, if we're going to try and do substitution again, we can't use u again because we're already at u, so we'd have to use a different variable, right? W, P, something like that. But I still don't, at this point, I'm not sold on the idea that I see something in its derivative. I mean, I see u, but didn't we say don't replace the variable with exactly the variable, like don't replace x with u? I'd have to go for a little more than that. I could say let w be u plus 1. What's the derivative of that? So if w is u plus 1, what would the derivative of w be? d1 du, wouldn't it? So I'd be able to, do y'all follow that? Okay, so this would be replaced with dw. What would this be replaced with? What is that? W, square root of w? And then what would u be replaced with? Oh, man. This is actually the correct way to do it. But do y'all see why this doesn't seem very natural, but I'm trying it anyway to see what happens? Watch what's going to happen. Everyone okay with this as substitution? That's what I've chosen, right? Taking a swing. I've got this. Now, I know that I can replace my u plus 1 here with what? W. I'm good on this. Du is going to be replaced with dw. My u is the only one still in question. But this is an equation, isn't it? This is a relationship. I can solve that for u, and it becomes u is what? W minus 1, right? So I can replace this, get out of there. This u right here is going to replace that. So my new integral, I'll keep the 1/2. My u is going to be replaced with w minus 1. The bottom is going to be replaced with what? square root of w, and then the du is going to be replaced with dw. And does that help me at all? W minus 1 over square root of w, and then dw. Why does that help me? Because now I can split them into two integrals. Because now I have two terms in one term. That's just the power of w, isn't it? This will be w over root w. This will be minus 1 over root w. So now I'm here. What is w over root w? Well, that's w to the first power over w to the 1/2 power. I'll write it out. We've come this far. Minus 1 over w to the 1/2 power, dw. Sorry, I'm going to go a little long here today. 1/2 integral of w to the 1/2 minus w to the negative 1/2 dw. So right here to here, this is what we did like first problem today, right? Split it up and then got powers. Now find antiderivative of each one of those. So what's our antiderivative of this? So you add 1 over 3/2, so that's 2/3. 2/3. 2/3 w to the 3/2 minus this one, 2w, 2w to the 1/2. Then all of that times 1/2 plus a constant. Did I lose you, or are y'all still there? Now let's multiply through. So we've got 1/3 w to the 3/2 minus w to the 1/2 plus c. But what's w? What's w? Go back and look. What was w? U plus 1 to 3/2 minus u plus 1 to 3/2, 1/2 plus c. But what was u? What was it? X squared? So 1/3 x squared plus 1 to the 3/2 minus x squared plus 1 to the 1/2 plus c. Box it up. I think a problem like that gives you some indication of where we're headed. All right? So for your homework, I recommend you do numbers 1 through 35, 1 through 36. This is page 307. 1 through 36, all of them. I suggest you do all. And I will also add to that, you should start with odds. Okay, do your odds, and then do the evens. Because the odds, you should have the answer in the back at least. Be careful with Wolfram Alpha. Okay, Wolfram Alpha is going to get the right answer, but it may not look like the answer that you're getting. That doesn't mean you're wrong. It just means that Wolfram Alpha is using a different approach. Okay? All right, sorry to keep you over, but I think that was worth it. Everyone feels good about that, right?